Okay, hello everyone. My name is Justin. This is going to be the very first of what's hopefully a thriving series of lectures about Haskell. One, I love Haskell, and I teach it to myself. By no means am I an expert. I've been doing this for about a year now, and I've noticed there's a lot of really just disjointed information. Some of it's really good, some of it's not good. Some of it is good, but it's a little it's frustrating because it's very difficult. And in particular, I'm thinking of the CS, I think 194 lectures that are famous in the community, but those are really difficult. It's probably difficult because we don't actually have access to the recorded lectures. We just have access to the lecture notes. Nonetheless, I hope that this video can maybe help someone who was in my shoes when I first started and go through a lot less frustration, right? And I think I know enough now where I can explain it. So prerequisites for this. All you got to do is install this thing called Prelude, which I will go ahead and link in the video description. It's completely free. It works. I'm on Windows, as you can see, but it works whether you want a Windows, whether you want a Mac or a Linux. You can get it in either of those ways, right? And I also am going on a book. I'm not going to share the book because I think there's like copyright issues. The book costs about $50, so it's kind of on the pricey side, but it's well worth it. And I am not being paid to say this, right? I'm just recommending and plugging this book because I think it's good. The book is called, hold on, Haskell Programming from First Principles, right? It looks kind of like this, right? It's purple. It's got some weird designs by a Christopher Allen and a Julie Moronuki. I hope I pronounced your name right. Forgive me if I didn't. But pure functional programming without fear of frustration. I'm going to be using this as a reference. Using a lot of examples from this. But I don't think I can really share the book. But I'm being all respect to the authors of this book, and I am plugging it for you. I'm going to use it as my guide here. As you can see, it's got all kind of great chapters about everything. It's amazing. It's very accessible. Whether you're an absolute beginner, you're coming over, you're experienced like Java, Python programmer, C programmer or something, it doesn't matter. You can follow along with this. It has plenty of exercises to work through, which we are going to be working through some of them. Highly recommend it. It's $50, but it's $50 well spent because I've never found a guide anywhere else on the internet as good as this one. But enough praising that, right? Let's get to it. So let me go back to the page I was on. All right. So you're in Prelude, right? Let's go. This is just kind of like the command line, I guess you want to say. It's something called GHCI, Glasgow Haskell Curry Interpreter. And then it has this thing called Prelude. Prelude is like the standard library of functions and packages and so on, right? That's all it is. And so, much like any Python, I'm most familiar with Python. You can do basic arithmetic. 2 plus 2 equals 4. 2 times 4 is 8. Now, the Haskell does have some quirks to it. For example, 2 times... Anytime you do a -1, you got to put parentheses around it because of the way it's called infix operators, which we'll talk about later, but it's just the precedence of how the operators are bound. The minus sign is unique. We'll get more into that later, though. Don't worry about it right now. You can do 2 times 100, gives you that big old number. You can do 10 minus 5. You get it, right? So on and so forth. There's some cool things you can do. You can also do some basic Boolean operations. 7 is less than 9, true. 7 greater than 9 should return false. Boom, it returns false. That's just, some examples of things you can do. Basic arithmetic. Just, you can play around, pause the video, play around with it if you want. Get comfortable with it, right? Now, I'm not actually going to do this, but if you ever want to quit, you type in : is like what gives you your commands to actually interact with the program, right? The GHCI commands. :Q is quit. That's not Haskell code, right? That's just a feature purely of the GHCI. It is not Haskell code. Info, or so let's say 5. Info 5. Nah, okay. We'll come back to that later, right? So we're going to be working through source files, which I already constructed the first one here, right? This is going to be our first official Haskell file. Consider it your own source code that you wrote. It's very basic. This is what we call the Hello World program, right? So it looks a little different than probably what you're used to if you're coming from another language, but I'm going to break it down, right? So every function in Haskell has what's called a type signature. So I'll do another video on this when I get a tablet or something to draw on, but you got to ask yourself, what is a function, right? Because Haskell is a functional programming language, meaning it relies heavily on functions. A function is a relationship between two sets, right? You call one the domain and one the codomain, right? And so it takes something as an input and spits out something else as an output. Takes an input from one set, spits out the output from the other set. Furthermore, functions are consistent, meaning that if I put the number 1 into the function, let's say x plus 1, so let's say our function f can be defined as f of x plus 1, kind of like f int, let's say f of x equals x plus 1. And I know I'm not using a type signature here, but like f of 1 is always going to return 2. F of 2 is always going to return 3. So in other words, f of 2 doesn't return 3 today, and then tomorrow it decides to return the number 4, right? F of 1 doesn't return 2 today, and then yesterday it returned 3, right? That's not how it works. It always, as long as the input's the same, you can always get the same output. That's very, very one of the core lessons you need to learn. Same input always leads to the same output. A function takes one thing and spits out another thing. But what is it taking in? What is it spitting out? That's what this type signature helps us with. So we have a function, we call it say hello. And by the way, I don't know why they do it like this, but in Haskell we use the camel case, which means it's written like this as opposed to say hello. That's called snake case. And that's how you do it in Python, but that's not how we do it in Haskell. To be honest, I don't know why, but that's just how it's done. Underscores do some weird things, but yeah, anyways. This double colon is what tells Haskell that this line is a type signature. So it says this is a function name. This is a type signature. In other words, it says this function say hello has the type. That's what double colons means, has the type. Now, what does this part mean? I'm not going to belabor too much on it, but if a string is more or less the same as what you think of a string in Python. It's a list of characters, right? That's what a string is, the literal definition. So this function takes a string. This arrow means that it takes this and spits out this. We'll get more into this. Don't worry about the syntax. Just know that this tells, and I'm not going to explain I/O right now. It's way above where we're at. I/O means input output, because this is a hello world program and it's printing something directly onto the screen. We need an input output monad, but don't worry about that. If that sounded like gibberish right now, perfectly fine. Just know that this thing is called type signature. Now again, on the second line, that's our actual function. So our say hello function takes one variable of a string type. We'll call it x, and it equals, what does it equal? Haskell, like Python, the indentation matters. So if you're allowed to break down and do it like this as long as you indent it with 2 spaces. Put strlen, what does that mean? We'll get into the specific meaning of it, but for now, it's a print function. That's all you need to know. For those who are new to computers, a print function is something that literally prints it out onto your screen. It displays, and we'll get into it later. Just know it's If you don't know what a print function is, it just means it spits it out on the screen at you. You'll see what I mean. And double quotes, remember, I know in Python you can use single or double quotes, not so in Haskell. Single quotes have a very special meaning for characters, right? The double quotes is for strings. So this is the string hello, comma, space. This plus plus means concatenate. If you're from Python or someone else, it more or less works the same way, pretty much. For those who don't know, concatenate means when you have two lists, it just kind of smushes together the things that are in the list. You'll see what I mean here. So it says, hello, concatenate whatever x is. See, x is our input. And then concatenate again with just this exclamation part. So pause the video and think for a moment, what do you think this function is going to do? We'll load it up and we'll see what it does. Okay, hopefully you pause the video. And now we're here, so I'm going to :L or load. You can shorten it to L if you want. No modules loaded, so let's say if we go to F of 1, oh, it got rid of that. Okay. If you ever want to clear all the modules, you just hit :L. Clears it. But we want to load our file. And just as a side note, you want to make sure you are in the same folder when you start GHCI, or if you want, you can do a :CD for a change directory to go to the folder you want to load it from, right? But anyways, we're going to load. We called this test.hs. So I'm in a folder, and in a subfolder, chapter 1, this is what we're on, test.hs. So let's say, and you can see here it's got this little star and it says main. That just means it loaded. So say hello, Justin. Hello, Justin. That's kind of cool. What if we did this? Double quotes with nothing between it is just an empty string, and I'm doing this to show you a point. So if you said, oh, it just inserts my name into X and then puts an exclamation at the end of it and then the hello at the other side, you know, so like smushes this, and X is my name, and then the exclamation point, you'd be correct. It's a hello world. We could do, say, hello world. Hello world. There you go. But look, notice what happened when we did this. Did nothing, so he said hello, comma, space, and an exclamation. So imagine for a second that this isn't there. It's just that. Well, it's hello, comma, space, and an exclamation. Funny how that works, huh? Alright. So. And then notice here, it just spits this out. There's more to that, but you don't need to know that right now. So we loaded our function. Let's see. Expressions, right? So everything in Haskell is an expression or a declaration, right? So an expression can be like a value, a data type. It can be some functions that are applied to values. And these expressions evaluate down to a result, which in this case would be hello world, right? Expressions are just what everything in functional program is about, right? And you also have a declarations. That's where you like assign something. So let me give you an example of an expression. 1, the number 1. 1 plus 1 is 2. That's an expression. Plus is a function, by the way. Icarus. It's an expression. It's a string. It says Icarus. Right? So you enter it, and notice here, like, okay, the number 1 is just the number 1. It doesn't reduce. Well, it doesn't reduce anything. But notice how this one, 1 plus 1. So in other words, this function plus. Because you might think of all operators like multiplication and addition in that as like something special, but they're not. They're functions. Everything is a function. And it simplifies it, right? That's what we mean by evaluate. It evaluates this down to 2. And again, this is just the same, right? Right, so now let's do another example, another easy example. 1 plus 2 is gonna, we all know it's 3, but watch. See, this is not it can the Haskell compiler knows it can reduce this to 3, at which point it can no longer be reduced. And the reduction terminates with 3 because there's no more terms to evaluate, right? There are no more terms to evaluate. Expressions can also be nested. What do we mean by that? 1 plus 2 times 3. Okay, so in other words, follows the basic order of operations when you do that with parentheses, right? So this tells it, let's look at what happens if we do 1 plus 2 times 3. You get a different result. Because order of operations says multiplication takes precedence over addition. And there's a way you can see that. I'm getting a little ahead of myself, but, or what is it? Info. Infix L6 plus. What does that mean? Okay. The infix is the exact order of precedence. So let's do info. So see how infix and L means it evaluates from left to right. There's also some things that have an infix R. We'll get to that later. But for now, look. This multiplication is from the left. It has an infix value of 7, right? And so all this does, it means since 7 is higher than 6, this evaluates. But what if we do info? I don't know. If the infix is higher, it means it evaluates before it. But parentheses have a higher precedence than everything, right? Or we could do 1 plus 2 times 3 plus 100, or 1 plus 2 times 3 plus 100. See? It evaluates from the left, so really this outer set of parentheses is kind of unnecessary. And then finally, when you get from an expression like this to just the number 109 or whatever the case, we call that a normal form. It's reached an irreducible form. You cannot reduce this expression any more than the number 109. Another example, 5 minus 4. 1. It is a normal form. Can't go any more than 1. Right? Now, we talked about Haskell's a functional programming language, so therefore, we talk about expressions being the most basic unit of Haskell, right? Well, what makes Haskell special is that a function is just another type of expression, no different than this, or this, or this, or this. And so we already talked about the definition of function. It always returns a result. Yep, every function in Haskell is important. It takes one argument and returns one result. And so this is kind of tricky because let's do, let's say g of x, y equals 2 or equals x plus y. Okay, then don't worry, well look, this says 1, look, our function here is 2 variables, right? And we just said that a function always takes 1 input and spits out 1 output, right? But oh, didn't we give this 2 variables? We'll get more into this later, but that is what there's something called currying, and it's basically more or less what it means is this function doesn't take actually 2 variables. It takes y and applies it to this function gx, and then that's resolved, and it's resolved this way. But we'll get to that later. Don't worry about it right now. I might be getting a little ahead of myself. So let's say that you had a function and you needed to like multiply it by 3, right? And you had a bunch of different things you wanted to multiply by 3. It's kind of a trivial example, but whatever. So let's say you had 1 plus 2 times 3, 4 plus 5 times 3, 10 plus 5 times 3, and so on, right? But you don't want to take that out every time. That's a waste of your time and your effort. You can make a function because it has a pattern, right? The pattern is call this x, call this y, x plus y times 3, right? So we want to think about things as a function, right? We got to think about what parts are common to every expression and which parts are different, right? So in this case, the parts that are different here are the 10 and the 5, or these two things, right? In this case, it's 1 and 2. In this case, it's 4 and 5. In this case, it's 10 and 5. If we think about something functionally, that might be a hint. Oh, maybe those were what we want to make our variables, right? But what stays the same? The parentheses stay the same. The plus always stays the same. And the times 3 always stays the same. Interesting, huh? So now we're going to learn how to define functions, right? We already kind of went over that. And so functions first start with the name of the function, right? And then the functions add the parameters, and there's only a white space separated. So in Python, where you might say like def, or you might say def f x y equals blah blah blah. In Haskell, we can just say f, well, we'll call it triple actually. Triple x equals x times 3. Right? And so here we go. This triple is what we call, is the name of the function. That's what we call the function declaration, right? It always begins, every function declaration must begin with a lowercase letter. And then, 2, here's the parameters of the function. In other words, the variables, right? And then we use this equal sign to define the function. Or in other words, to declare the values in the functions. Note this equal sign is not how we test for equality in Haskell. That just means separate. It's a in the context of a function, it's a separator. It says, all right, this is our function's inputs, and this is function name, input, and this is output equals how you separate them, right? And then for the body of the function is the expression that's evaluated when it's applied, right? So if triple is applied to some value, then it's going to necessarily do it in this fashion, right? So let's see. Let's do an example. Triple 1. How does that work? 1, we take x and we substitute 1 for x. And then on this side, we also take, anytime we see an x, we substitute a 1. A 1 times 3 gets us 3, right? So triple 2 is going to be, drum roll, triple 2 is going to be 6. Triple 3 is going to be 9. Now let's triple. Don't worry about the type signature so much. Just know that this takes an integer and spits out an integer. So we said triple x equals 3 times x. What if we wanted to do 3 minus x? Let's see if that would work. So let's go L testa hs triple 3. Oops. So I was in chapter 1.test.hs. Okay. So triple. Remember, now we changed triple to do minus. So let's see. Triple 3 is 0. What about triple 0? Triple 0. Triple 1 is 2. Because 3 minus 2 is 3 minus 1 is 2. Triple 2 is 1 because 3 minus 2 is 1, and so on, right? What else? So yeah, that's basically how functions work there. Right, so Haskell, now we're talking about evaluation, right? Haskell uses something called a lazy evaluation, non-strict evaluation. It means it holds off on, that means is it's lazy. It holds off on evaluating something until the absolute last possible minute, until it's forced to. Right? So values are irreducible, but the applications of functions to arguments are reducible, right? So if reducing an expression means evaluating until you're left with a value. So in other words, number one, the word hello, those are values that cannot be, they're expressions that cannot be reduced further. These are values. What I'm about to type in are expressions that can be reduced to a value. See? You see the difference? It's pretty easy stuff. Alright, so now we're going to finally get into some problems. Some quick exercises, right? So let's go clear the screen, clear the prelude. So this says, I'm going to drag this over here. A comprehension check, right? Given the source, following lines of code as they might appear in a source file, let's say that, half of x equals x divided by 2. Square of x equals x times x. So we want to write those same declarations in our REPL and use the functions half and square in some experimental expressions. So let's do that. Half of x equals x divided by 2. Square of x equals x times x. Let's say half of 1. Oh, interesting. It spits out 0.5. Not a fraction, it spits out a decimal. As you will learn, Haskell's very picky about types. And there's I think 5 different types of integers. You'll see. But don't worry about that right now. Just something interesting I wanted to show out. What about half of 2? Oh, look at that. That's interesting. 2 is evenly divisible by 2, but it still spits out a decimal point. Wonder why that is. Fractional A to A. Don't worry about that right now. That's why. I'm getting a little ahead of myself here. What about square of 1? Square of 2? Square of 0.5? Oh, interesting. So when you do whole numbers, it spits out whole numbers. When you do decimals, it spits out decimals. It's kind of weird. What if we can combine these? That's interesting. Half square 2. Let's say, half of square of 2. Square of half 2. What does that mean? This is called function composition, right? So we start with the square of 2. So in other words, let's take 2, put it into x. It spits out 2 times 2, which is 4. Then we take this value, and we in turn put it into here, into the half. So now we have 4. What is that? We put 4, substitute x with 4, so 4 divided by 2 gives us 2.0. But if we reverse it around, we kind of do the opposite thing, right? So we start with the half of 2. So in other words, take 2, substitute every instance of x for 2 in the half function. 2 divided by 2 gives 1. And then we go substitute that here. So now we have square of 1. And we substitute 1 times 1. There you go. That's how you get that. Isn't that cool though? You can apply a function and use it as a variable of another function. That's pretty powerful stuff. Alright. Now what does it want us to do? It wants us to write one function that has one parameter and works for all the following expressions. So 3.14 looks like that's a common theme. Looks like this external multiplication is a common theme. And looks like we have some number times itself. That sounds like a familiar formula. That's the formula for the area of a circle, pi r squared, right? That should give you a clue. So let's write a function that takes this approximation of pi, call it 3.14, and multiplies that by a number times itself. Pause the video, try and type it out yourself, then we'll go over it. Okay, hopefully you paused the video. Now we unpause it. We're going to call our function radius of, we'll go with y. You can use an x a lot. So we had a 3.14, because that was, everything was always times 3.14, times, and then parentheses. And remember, it was whatever y is squared, so y times y. Let's see if we get that. Radius, first expression was 5. What happens if we do 3.14 times 5 times 5? We get the same thing. We can do it for radius 10. 3.14 times 10 times 10. Same thing. 3.14 times 2 times 2. Radius 2 is the same, right? So we pretty much distilled that pattern. In other words, let me show you. We looked at all these, found the common pattern was that it was just some number times itself times 3.14, and boom. Number 3 says there is a value in prelude called pi. Rewrite your function to use pi instead of 3.14. Let's just, and you can do it like this, right? Radius of y, pi times y times y. Radius 5. Look at that. Instead of being precise only with one decimal, it's precise to a lot. Radius 10. So this looks like it rounded down. So this is, you see what I mean? It only at 1 point of precision. If you remember, we used a caret operator too, so you could also find radius y equals pi times y squared. Let's see if that works. Radius 10. Okay, you get the same thing. Radius 5. You get the same thing. Cool, we're Gucci. That proves that there's more than one way of doing a function, right? We already talked about the infix operators. Okay, yeah. So we have two kinds of functions, right? There's prefix functions and infix functions, right? So for example, the triple function we have is like triple 3. In other words, the function name came before the number 3, right? Or with the radius function we just did, right? You could have ID as the identity function. Just spits out the same thing. But if you notice, remember we said everything is a function. Some functions have the infix style. Particularly operators. Operators are functions that can be used in the infix style. What do we mean by that? 3 plus 3. Remember, every operator is a function, but not every function is an operator. So triple, ID, and radius, those are prefix functions. This plus function is a infix. Means it just goes in the middle of it, right? Instead of going before it, it goes in the middle. That's what that means. So we could do 100 plus 100, 7, 6, 8, 3, 9. 2, 1, 3, 5, 6, 5. See how that goes? You put these, but what can we do? I don't know. Now there are some functions. We can make certain functions have an infix style. So let's say div 8.4. All right, so div is a division function. It's different than this because look, 8. But that's a little confusing because we usually think of division as an infix operator, right? So there's a way you can fix that. Instead of writing it like this, you can write it like. So if you want to turn a prefix function into an infix function, you just put those little backwards dashes around it, right? And then similarly, it'll be significant sometimes. Let's say you want to use this multiplication as a prefix function. All you do is put it in parentheses. So 768,395, 21356,345. It's the same. Even works with the minus, right? That's just different syntaxes, right? All right, so then you got associativity and precedence. We already talked about. That. So yeah, let's just review it real quick. Where is it? Right. So infix, it means an infix operator. It has left associativity as a precedence of 6. So the higher the precedence, it goes from 0 to 9. The higher the precedence, the sooner it's applied, right? And then in the infix function name is just plus. What about if we wanted info minus? Same deal. Left associative, infix function, precedence of 6, that's the symbol. What do we mean by left associative, right? 2 times 3 times 4. What we mean by left associative is that expression right there is the same as this. In this case, multiplicative is what we call, multiplication is what we call abelian. So in other words, it's, what we mean by abelian is 2 times 3, 3 times 2. You can flip the elements around, it doesn't matter. Now, some functions, let's see, 4 minus 2 is different than 2 minus 4. Is not an abelian operation. I think there's another word for it, but I know it from group theory. It's abelian, right? It's not the same. But let's look at an example of right associative function, right? Okay. Now, so you notice how we go up here and all these were infix L. This one is infix R, meaning it's right associative, has a precedent of 8 as opposed to 6. So in other words, this exponent operator would take precedence over plus and minus and multiplication and all that, right? It's associative from the right. It's an infix operator. So let's do this. 2 times 3 times 4. That's a big-ass number. What we mean by right associative is this. So the parentheses goes from the right to the left. That's what we mean by right associative. As opposed to left associative, because watch what happens when we do this. Much different, huh? Think about it, though. It's right associative. So let's say 3 to the power of 4. So 2 to the power of 81 is that big number. What if we do it left associative? 2 cubed is just 8. 8 to the power of 4 is just 4096. See how that makes a difference? And really, if you remember PEMDAS, that's pretty much true. That's pretty much true, right? So, all right. He wants to say, are these going to be the same or are these going to be different? What do you think and why? Pause the video, try these out, and we'll go over the solution. Okay, hopefully you paused the video. Work those out on your own. Let's try it out. 8 plus 7 times 9. 8 plus 7 times 9. They are different. Let's look at something. So info plus. Look at this. We know they're different because they have a different infix precedence. That's why it had to be that way. That's why the parentheses made a difference. Second example was this perimeter function. Let's see, perimeter xy equals x times 2 plus y times 2. Oops. We'll call it perimeter prime xy equals x times 2 plus y times 2. Perimeter 1, 1. Perimeter prime 1, 1. Perimeter 2, 1. Perimeter prime 2, 1. Perimeter 1, 2. Perimeter prime 1, 2. Oh, farther. Let's do the ultimate perimeter minus. Remember, we have to do minuses 5. Perimeter prime minus 1, 5. Looks like they're the same. And if we go to that, look, multiplication happens before addition. So you don't really need the, they don't harm anything, but you don't need the parentheses here. Just because this is already going to resolve itself because look, the infix precedence. The infix precedence takes care of that for you. Now what if it were x plus 2, let's see, 1, let's do perimeter xy equals x plus 2 times y plus 2. Perimeter prime xy equals x plus 2 times y plus 2. See, they're different. That's because this infix operator is lower than the multiplication. So in this one, it's saying first multiply 2 times y, then add x to 2 plus y, and then add x plus 2 times y to 2. Whereas in this one, it's saying, all right, first solve x plus 2, then solve y plus 2, then multiply them together. See the difference there? And then finally, f of x equals x slash 2 plus 9. F of x, we'll call f prime of x equals x slash f of 1, f prime of 1, f of 11, f prime of 11. They're different, right? Because again, info let's compare these. Different infix precedent. Again, same thing. Same thing as the other one. That's why it works out that way. Alright, so here's an interesting thing. Order of declarations in a source code file doesn't matter because GHCI loads the entire thing at once. But when you enter things one by one in the REPL, the order does matter because it's not coming up all at once, right? Let me give you an example of that. Let's say y is equal to 10, x is equal to 10 times 5 plus y. My result equals x times 5. Interesting. And what about x? What about y? So it looks like y is 10. It's easy enough. X is 60 because 10 times 5 is 50, plus y, which we said is 10, plus that is 60. And then my result, this value, is just equal to whatever x is, which is 60 times 5, which is 300. Makes sense, right? Now, let's do something a little different. Learn.hs module learn where x equals 10 times 5 plus y. My result equals x times 5. Y equals 10. Now I'm going to pause this and I'm going to save it. Okay, so now we're going to go to load chapter 1 / learn.hs. Okay. So remember, we did it in a different order here from what we did in the REPL. In the REPL, we started with y, and then x, and then my result. In this, we switched it up. Let's see what happens. My result is 300, y is 10, x is 60. Interesting. Let's write them in the same order here. So I'm just going to copy this for be lazy. Oh, look, variable not in scope. Because we haven't defined a y. Haskell doesn't know what y is. That's why we had to define it up here as that, right? That kind of tells you about that. I hope that makes sense. Source code is, we already talked about spacing. Spaces we already talked about at the beginning. Just don't use tabs. Use spaces explicitly. Okay. I'm going to put this on the screen here. Okay, so we got this exercise. Sample codes are broken and won't compile. These two are what we get in the REPL. And then this one is what we get in our source file, right? So we want to fix these mistakes. Pause the video, try it out on your own, unpause, and come back and we'll do it. All right, we're back. Let's try this. I'm going to literally copy this verbatim. Oops. This one said the REPL. Union type variable MBC for all BC. And what the hell does this mean? Oh, look, we got a space right there. I might want to fix that. So, oh, it works. Area 1, area 2, area 5. There's the space there. What about the second problem? Variable not in scope, B. Well, that tells me that's pretty easy. That should be an X because we defined it. You can do it one of two ways. You can change the X to a B or the B to an X. It'll work either way. Watch. Double X equals X times 2, double 1, double 2, double 3. You get the point. You can also do double B equals B times 2, double 1, double 2, double 3. It's the same. As long as these are consistent, that's how you fix them, right? Now this one tells us we have to load it into our notepad here. And this one, I didn't paste all the way, so that was the issue here. Add a space there, see? So we're gonna save this as, let's see, indentation.hs. Oops. Oops. L. Parse error on the input equals. So let's go back here. Look at that. Remember, we said Haskell's very picky about spacing. Let's move that back. Get these all online. Try that again. Oh, look, it works. So y was 10, x was 7, f was x plus y, which is 10 plus 7, 17. We're in the business. Pretty simple. All right, arithmetic functions in Haskell. These are very important, right? So we feel like we know these ones, right? But what is div, mod, quote, and rem? Oh boy, we'll get into this later, but div and mod go together like quote and rem go together, and integral vision rounded down towards 0. These two, div and mod, will always return the same values as quote and rem when the inputs are positive. When they get a little different is when they're negative. You'll see what I mean here in a minute. Okay, so 1 plus 1, 1 minus 1, 1 times 1, 1 divided by 1. What about 1 div 1, 1, mod 1, 1? Mod is like modulo, works the same way as from Python, right? Like a remainder. What about quote 1, 1, rem 1, 1? See, when the numbers are positive, it works. Let's try something different. Let's try div 2, negative 1, mod 2, negative 1, quote 2, negative 1, rem 2, negative 1. Actually, let's do better. So div 7, 3, 2, mod 7, 3. Actually, 7, remember we're going to do infix. So 7 div 3 gives us 2. In other words, 3 goes into 7 2 times, rounded down. No cut the remainder off. What about mod? 7 mod 3 is 1. Now notice something here. 3 times 2 is 6, plus 1 is 7. So in other words, there's a relationship here. Let's look how quote and rem work. So 7 quote 3, same. And then 7 rem 3, 1. So the remainder and the mod. It's all the same when it's positive. You can try it around yourself. Let's see what happens when we do negative. Negative 7 div 3. That gives negative 3. That's interesting. You just think of it as if you're doing negative division. It's like 3, negative 3, negative 6, negative 9. Negative 9 is beyond 7. That's why you get a negative 3. And then mod is going to be 2. Watch. Oh, it's 1. Hold on. Just we'll get more into that later. It's complicated to explain, kind of. Oh, that's why it was that. Okay. So what if we do -7 mod 3? Yeah, exactly. So 3 times -3 is 9, plus 2 is -7. -7, quote 3. So look, div in this case is -3. Quote in this case was -2. And this is -3 times -2 is -6, -1 is -7. That's the relationship. If that blew your mind or you're a little confused, don't worry right now. It's fine. Just a little skipping it ahead. Yeah, that's exactly what I said. Quotient of x and y times y plus the remainder is always going to be equal to x. And it's the same here. We kind of talked about that, right? Negative numbers, right? That works if it's just one number by itself. But what if we want to do 9 plus -1000? That's not going to work. Because negative, so subtraction is the same precedence, right? If we want to do that, we just have to do 9 plus. There we go. That's how you do it. It's that simple. So really, when you have a number like this, but we call it syntactic sugar. It's just a more elegant way of saying negate 1000. Instead of having to type out negate, you can just put -1000. It's the same. That's really all that is there. We already talked about parenthesization. Yeah, I'm getting a bit burnt out of this, so we'll continue to lecture next time. Hope you enjoy.